so here we have a compressor. Okay, it has an inlet and an outlet. We call it suction inlet and a discharge. Now, when the gas that's returning from the evaporator, so the gas direction is this way, and that might be at, say, just pick up the pressure at the moment, I'm just going to use 400 kVA, right, and we're going to go to this one here. It's going to push the gas up using a piston through a cylinder, and it's going to discharge it out here, and let's just say that's 1700 kVA, yeah? So that's a much higher pressure. So the delta P, the difference in pressure between those two, is 1700 minus, so delta P, 1700 minus 400, which is 1300 kVA difference. Now the ratio, without getting too technical, all that over that, I won't go into adding, is called the compression ratio. So the higher that is and the lower that is, the higher the compression ratio. Alright, so then the direction here is there like that as well. And the gas comes out when the piston's at top dead centre. It's pushed the gas out and it's sitting at 85 degrees, around about 1700 kVA. And it goes through the discharge line, which is the hot gas line, and then it enters the heat exchanger called the condenser. And then the gas inside the pipe is cooled down by the air blowing on the outside of the pipe through the fins. So this one's got fins as well, it's like a radiator. And we lose temperature in the gas as it gives up its heat to the cooler air. Now the air, maybe 36, depending on the outside conditions, 37, 38, whatever, but it's still a whole lot colder than 85 or 84 degrees. So we're losing sensible heat here in the refrigerant gas. It's 100% gas, 100% gas, 100% gas, but we can see how it's losing heat. It's superheating as it goes through the coils. And it continues to cool down by virtue of the fact I've drawn it in different colours until it gets to a temperature where it stays the same. And that's the latent heat phase. That's the phase that plateaus out. So it's de-superheating here, gets to 46 degrees or so, and then it stays flat. And what's happening is, as I said before, as it gets to the 46 degrees, it's condensing. It's going from a portion of liquid from a gas, so it might be here, say 5% liquid and 95% gas, 10% liquid, 90% gas, 20% liquid and 80% gas, 70-30, 60-40, 50-50, until eventually the percentage of liquid is outweighing the percentage of gas, 90%, 95% liquid, 5% gas, until it's completely a liquid, and say, theoretically it could be anywhere along there. As the air continues to take the heat out of the refrigerant, it completely condenses, and then the latent heat phase is finished. So we see the 10% liquid, 20% liquid, 30% liquid, 40%, 50%, till it gets to 100%, and then the temperature starts dropping again. So that's subcooling underneath the boiling point, underneath the saturation. Right now we can get a change in temperature again. De-superheat, latent heat of condensation, that's where it's changing state from a gas to a liquid, and then it's subcooling. Once it comes out of the condenser, there's no more heat exchange. It goes to the tank here, the receiver, where it stores the refrigerant and it provides a head for this. I'm not going to go into the technicalities of that, why and when we don't have it, and why we do have it. And then what happens is this high side of the system is now, that pressure is regulated through this valve. Now in this instance I'm only going to talk about it as being a fixed orifice. So it's going from a small pipe to an even smaller opening, and then when it comes out, it's opening up into a bigger pipe, so you get this expansion. You've got like a mist or an atomised spray which is coming out, which is liquid. Now the pressure's completely dropped. There's less force holding it as a liquid, so it begins to boil at 0 degrees. Up here, it was at that boiling state of 46 degrees, or later bit of condensation, we were stripping heat out of it. Now, because it's lower than the air temperature may be 24 degrees. The 24 degrees is a whole lot higher than 0 degrees refrigerant temperature inside the pipe. Now again, this is a latent heat phase, but this time the latent heat is in the reverse. It's going from a liquid to a gas. Okay? But it needs energy to do that, so it strips the air at 24 degrees of its heat. And the heat's transferred through the fins, through the pipe walls, into the refrigerant, warming up the refrigerant, allowing it to change state at a constant temperature. That constant temperature is the latent heat of vaporisation. So it's the reverse of this. And so we have, we're going to use the colours, we have a situation where as it's travelling through the evaporator, the indoor coil, what happens this time, it's going this way, we have 90% liquid, if the liquid's on the bottom line, and on the gas on the top, if we were looking at the ratios, 10, 80, 20, 70, 30, until we get to say 80% gas and 20% liquid, 90% gas, 10% liquid, until it's all boiled off. Right? Where's it boiling? Why is it boiling? Because the air that's hitting it is 24 degrees and it's giving its heat up to 0 degree refrigerant. While ever there's liquid present there, so there's our liquid 90%, 80%. As we're going through, we're expending it, we're using it up, right till we get to the point where we've got 99% gas and only 1% liquid left. That's near the end of the evaporator, and then when we get to 0% liquid and 100% gas, well, that's when we can start getting superheat effect and temperature rise. So if we would say that this point here represented where the last remaining little bits of liquid are boiled off into gas, then 0 here, 0 here, 0 here, 0 degrees C, because it's a constant temperature process. Unlike the radiator, which as it's coming down, it's actually gliding down, and the air's getting hotter. This is at a constant temperature, so we get a much more even distribution of heat coming off the coil. Then we'll see the temperature rise here, 3, 4, 5, 6 degrees. Right, from 6 degrees C, that's a nice temperature back at the compressor. Okay? And so the air goes on at 24 and might come off at 13. The air's cooled because it's given its heat off to the boiling liquid refrigerant inside the copper tubes. Right? And because it's 0 degrees, it's changing from a liquid to a gas, cold boiling. Remember? So copper boilers at, what was it, 2,562 degrees. That's very, 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 very hot. While water boils at 100, what do we say, liquid nitrogen boils at minus 195 degrees, which is extremely cold, but we can get our refrigerant boiling it at a specific temperature, say 0 degrees. And we do that by adjusting that pressure there. If we go lower, that pressure will drop. Remember that chart I showed you? Right, that pressure temperature chart? Drop the pressure, you'll drop the boiling point. Raise the pressure, you'll raise the boiling point. So if I make that 450, that may go up to plus 4 degrees. And if that's what you want, that's what you'll get. If you want to be colder than 4, you might make it 425. That will also drop to 2 degrees. Right? If because of inefficiencies, you're going to get some losses through the pipes and the fittings, you might want to drop it to minus 1 degree. So it might come in 400 minus 1, and then you risk getting a little bit of ice up. Once the ice starts, though, the air won't go through. So that's the Vapour compression cycle. Gas comes out, turns into liquid, is provided the liquid tube, the pressure drop valve, high pressure, very dense liquid, suddenly a low pressure, and very open. diffuse, a much more diffuse environment. That causes the forces on top of the liquid to be reduced, allowing it to boil into a gas. As it boils into a gas, it absorbs the heat of the air, and hence we get cold air on the other side, 24 on, say 13 on. Yeah, that's the answer.